Welcome to Module 3. Today we will discuss some basic codes that are useful to automate your data analysis. Let's begin. The learning objectives for this module include understanding the structure of functions, learning about the types of logical operators that MATLAB can use to index data, writing codes that employ logical operators to identify outliers, subset data, and plot data, and writing code to modify plots, and learning about adapting generated codes to import data, plot data, and compute new variables. Any expression entered into MATLAB should take the form of the following. On the left side of the equation is the variable name, and on the right side of the equation is some expression. We've seen this already when we've inputted data, for example, data 1. Functions take the same format in terms of syntax, but also have additional parameters for the input and output. Let's take a look at a couple examples in MATLAB. Here I have two data matrices organized as columns. First, we're going to compute a new variable called mean data1, which takes the mean of the first data matrix. Here we have one input and one output. The second thing we're going to do is we're going to compute the rows and column values using the size function. And we'll compute this for data 1. So again, we have two outputs and one input to this function. You'll see that row and column are now listed as separate variables in our workspace. Last, we'll look at the correlation function, which takes two inputs, in this case data 1 and data 2, and outputs two variables, the correlation coefficient and the p-value. Again, we see these additional variables in our workspace. Logical operators allow us to compare two Boolean values using the following comparison sign. Less than or equal to, greater than or equal to, equal or not equal. If a comparison statement or expression is false, then the answer will be 0. If it's true, then it's equal to 1. And you can also combine logical statements using the following: the ampersand for and, the straight line for or, and the tilde for not. Let's go through a couple of examples. First, recall that data 1 looks like this. So we're going to ask some questions about data 1. So the first question asks, in data 1, in row 5, column 1, is the value equal to 2? So row 5, column 1 is equal to 2. So this expression should result in a 1. The next expression asks if the value in index 3 is equal to 2. And we see that the value in index 3 is not equal to 2. So this expression should result in a 0. The last expression combines two sets of expressions. It first asks if the values that are in rows 7 through 9 in column 1 are greater than or equal to 1, and if those same values are less than 2.5. Here we see that we'll end up with 0, 1, 0, meaning that this value is not greater than or equal to 1 or less than 2.5, whereas the second value is, and the last value is not. The find operator is also helpful in indexing where data meet logical conditions. Let's look at the documentation for this function. The find function provides indices and values of all non-zero elements that may meet a particular criteria using logical operators. The syntax is as follows. I for index is equal to find of some value. There are a few examples here, but let's try some with our data. The first thing I'm going to do is I'm going to look within data 1 for any value larger than or equal to 2. And I'm going to call this index big. So this value will have all the indices or locations within data 1 where this condition is true. We can then use those indices and index within data 1 the actual values that are in data 1 that meet that condition. So again, data 1 looks like this. We're going to use find to locate any values that are greater than 2. So we'll see that index 3, 5, 6, 8, and 9 meet that condition. and we get those indices there. I can apply those indices within data 1 and create a vector of the actual values. So in this case, 3.3, 2, 3.6, 2.4, and 2.8. Next, we can combine logical operators to look for mid-range values. So I'm going to call this index mid. We're going to find any value that's greater than or equal to 2, but less than 3. And these are the indices of those values within data matrix 1. Lastly, the find command can also output rows and column indices. And this is very useful when we're using data sets that are quite large and we want to know exactly the location rather than the index. So here we'll get the idea of where the row and column will meet these conditions. So here I'm looking for small values in which data 3 is less than 1. And we can see that data 3 looks like this. And what we find here is that the value in row 1, column 1 is less than 1. Row 7, column 1 is less than 1. Row 1, column 2 is less than 1. And lastly, row 7, column 2 is less than 1. Logical operators and conditional statements become really useful when you're subsetting data, using loops or for a variety of different purposes. For example, if I'm only interested in looking at condition 1 data, I can subset my data, I can plot only those data, and I can compute the means all within one loop. Logical operators are also useful in identifying outliers. For example, where data within your data matrix are equal to the mean plus or minus 2 standard deviations. So let's go through an example. Recall that we already computed the mean for data 1. To identify outliers, we also need to compute the standard deviation for data 1. Now what I'm going to do is I'm going to create a set of indices called outliers using the find command. The first condition is that data 1 is greater than or equal to the mean plus or minus 2 times the standard deviation. Then we're going to apply those indices to our data and set them equal to NaN. So let me open dataset 1. And just taking a quick look, it doesn't look like any of these values will really meet that condition. But if it were the case, those data would be set to NaNs. And as you can see, nothing changed, so we don't have any outliers in this small data set. Let's shift gears a little bit and talk more about plotting. Although we have already created several figures using interactive plotting commands in the MATLAB windows, it's useful to be able to understand the structure of the plot command so that you can make changes directly to your codes. We have already changed the line styles, axes, text or annotations, color properties, and markers using the interactive functions. Here we see a couple of the basic plotting commands. This line also suggests that we can change what's called line spec, or line specifications. Here we see that line spec sets the line, style, marker symbol, and color. Here are a few of the examples of things that you could switch. You can change the lines from solid to dashed, the markers from a dot to an open circle, and the colors of the markers and the lines. In addition to creating single plots, we can also divide our figure window and create subplots. The syntax for this is as follows. The subplot command, you're indicating the number of rows and the number of columns with which you want to divide your figure window and the position of your subplot. Here the positions go 1, 2, 3, and 4. To create a subplot that spans the length of 2 positions, you use the colon operator. Now let's plot some actual data and put the values in a subplot. This first set of code opens a new figure window, creates a subplot with 2 rows by 1 column, and plots the first set of data in the first position. I'm plotting data 1, and I'm creating the X and Y labels for the different axes. I'm also creating a title, and I'm using the axis command to hold the axes consistent for the X and for the Y. And here we have our subplot for subject 1. Now let's plot subject 2. We're maintaining the same organization for our subplot, 2 rows, 1 column, but now we're plotting in position 2. And I can plot data 2 in the same way I plotted data 1. Again, using the axis command, I can make sure that both of these data plots are on the same range. And here we have our data for subject 2. In many ways, creating codes like this simplify and automate your data analysis pipeline rather than having to click through MATLAB's plotting tools. Let's go through an example of a workflow typical to the data analysis pipeline that you might do. First, we will generate a table of data using the import function, split our data by condition using logical operators, plot our data for visual inspection, customize our plots, adjusting the figure scripts that are output by MATLAB, create new variables, for example, computing a mean, and then plotting those means onto the previous subplots that we made. For this last section, I'm going to close the PowerPoint window and to maximize our MATLAB window. The first thing I need to do is import my data. I'll import my data as a table, I'll import my selection, and I'll also create a function that will allow me to import data of a similar organization. Here we'll see that our function is organized in a particular way. It calls subject1 or sub1 as our variable name. The command is actually called import file1, and it requires 3 sets of inputs: the file name, the start row, and the end row. MATLAB automatically generates the following sets of comments that are really useful in understanding the structure of this function. First, it says that by default, it just reads the file name and calls it subject1. You can also include the other parameters like the start row and end row. And it takes as an example the data that we already imported. So here, it's already imported subject1.text. It's called it that in the variable window. It starts at row 2 and goes to 2049. I need to make sure that I save this function. So I'm going to go to Save As. It will automatically call this function by the name that it created to begin with. So here it's called import file1. This function could also be changed if you have other functions that are similar in name. MATLAB does this in order not to overwrite previously existing functions. Now that I have subject1 in my workspace, I can use this import file1 function to import all the other data sets that match the same organization. And here I have 5 subjects. I'm going to import subject 2 through 5 using that same function. And here in our workspace we see that all of those data are now input. When I look at subject 1 in the variable window, we see that the first column is organized by indicating the condition. And in this case, I know that I only have 2 conditions, condition 1 and condition 2. I also know ahead of time that condition 1 is the first 1024 rows and condition 2 is the last 1024 rows. But say I didn't know what the ordering and the number of rows that index condition 1 are. We can use logical operators to determine which row, for example, subject 1 condition 1 equals 1, or subject 1 condition 1 equals 2. And then we can take those indices and subset our data using those indexes. So what this is doing is it's creating a new subject variable called subject1c1, in which we're taking all data from subject 1 for the indices that meet the condition equals 1, and all columns. I'm going to go ahead and do this for all of my subjects for all of the different conditions. Now we see that each of the different conditions are subset for each of the different subjects. Next, what I'd like to do is to create a meaningful way of describing the samples when we're plotting. Right now, if we were to create plots, the X range would be the indices for each of those different data sets. Alternatively, if I know the sampling rate with which I collected my data, and we know what samples in time correspond to our data matrix, we can create a time variable that's actually more meaningful. So for example, the data that we have here from each of these subjects are from ERP data, which means that these data represent the average of all trials with respect to a trigger or event. For example, the current data start at 1 second before and after this event. Therefore, I want to create a time variable that will start at -1 second and range to 1 second after the event, where 0 indicates the event time. Although these commands may be a little bit confusing, all you have to know is that I'm creating an index of values. I'm starting at -1 and I'm moving in increments of 1 over the sampling rate, which converts the sampling rate into time in seconds. And I'm moving to the end of the file, which is 1 second minus the sampling rate. And that should give me a total vector that's equal to 1,024 points. This time vector now corresponds to all the data that we'll be plotting for condition 1 and condition 2 for all subjects. Now what I'd like to do is plot electrode C3 by time for all subjects and for all conditions. We can do this using the interactive plotting commands. So let's do that here. We'll start with subject 1, condition 1. So now I'm going to create a plot of C3. And we've done this before, but now what I want to do is I want to use the Show Plot Tools and Dock Figure option. This will allow us to modify a plot a little bit more interactively. So if I highlight the first line, I can change the display name to subject 1. And instead of using auto, which is the index, I can now select the time value. And I make my axes a little bit larger so it's easier for us to see. We can see that our time range now goes from -1 to 1. And I can include an x-axis title now of time in seconds. And while I'm at it, I might as well also create a y-axis title. And this is going to be EEG amplitude. And I'll show you something cool. You can create Greek letters by using certain subscripts. So I have EEG amplitude and microvolts. Say I also want to insert a title, C3 for condition 1. Now let's go ahead and add some more data. So I'm going to select subject 2, C1, C3. I'm going to change the display name and continue adding data. Subject 3. We can also include a legend, which will designate which color the lines represent. Now here's all of our data for condition 1. Now let's say I wanted to create a subplot where I have condition 1 on the top and condition 2 on the bottom. Using this new subplot 2D axes, I can highlight 2 rows, and now I have condition 1 on the top row, and I can create the second figure below. For the sake of time, assume that I'm just going to use the exact same method of adding data to this new subplot using the add data command at the bottom. Once I'm finished, again, I can generate a MATLAB script that will allow me to recreate this figure exactly as is. Here's an example of the finalized figure. There are a few things to notice. First of all, the condition 1 and condition 2 are set for electrode C3. And this is fine if we always want to recreate C3. But maybe I want to plot another variable, say CZ. So that makes it difficult to apply these data. So we might want to change this in the hard codes. The second thing is that our y-axis ranges quite a bit between the two conditions. So maybe setting our x range to something that might capture both sets of data but keep them on the same range will allow us to visually inspect our data a little bit more carefully and compare conditions. So let's go ahead and modify some of this code. To modify this function, we have to do a few things. First thing is that we have to name it something differently. So now I'm going to call this custom create figure. And I'm automatically going to save this as custom create figure. And this way I won't overwrite that previous figure script that I created earlier. So what I'm going to do is I'm now going to add a variable called electrode. And this electrode variable will allow me to specify which electrode I want to analyze. The second thing that I want to do is I want to change the titles so it no longer has C3, but it calls this electrode electrode value. As long as electrode is a text or a cell, we can include this in our title. I'm going to remove the C3 component and just write the name of electrode. Now, if I'm trying to analyze CZ, that value will go into here and allow me to concatenate this with our other string of condition 1. And I can do that for both subplots. The last thing I want to change is I want to change the axis range. So after I've plotted condition 1, I want to use the axis command to set the x and y limits of our axis. In this case, we're going from -1 to 1 in seconds. And let's say we're going to go from -50 to +50, which seems like a reasonable range for these data. I'm going to copy this axis command again to the bottom of the file. And now I'm going to make sure that I save this as custom create figure. Now when I call custom create figure, I have to make sure I include this electrode value. Now when I call this custom create figure, I'm having my time as my x range, the subject data for subjects 1 through 5 for electrode CZ or CZ, and the second set of conditions for subjects 1 through subject 5 for CZ, and I'm indicating that the electrode is called CZ. When I run this code, we now see that the Y range is listed as 50 to -50, that CZ is now listed in the title for the condition, and we now have an adaptable script that can be used to analyze condition 1 and condition 2 for 5 subjects for all data. One thing that might be helpful is to plot what's happening in terms of the whole group. So what I'd like to do next is I would like to compute a group mean for condition 1 and condition 2, and then overlay that onto this plot. And we'll do this for electrode C3. So the first thing you'd like to do is for us to find help on the nan mean function. And nan mean is really useful when you're trying to compute means for data that have NANs. And here we see the syntax for the nan mean function. It computes the means for values x after removing NAN values. Importantly, it also has this dim value, saying it takes the mean along the dimensions of x. In the code that I have here, I'm taking the means across the dimensions of x, which is 2, so across the columns. So for each data point, we'll have our data from each of these different subjects, and I'm going to compute one mean for that time point. That will allow me to create a group-based ERP that I can overlay onto our individual data. I can do the same thing for the standard deviation if I'd like to. For now, we're going to focus on the mean, but I'll go ahead and write these data to the workspace. Now what I've done here is I've created a custom figure called custom create mean figure, and I've added 2 more inputs, y mean 1 and y mean 2, which are the matrices for data mean for data condition 1 and mean of the data condition 2. Here I've added an additional plotting to plot the mean as a black line with a thicker width for condition 1, and the same thing for condition 2. Now I can call this function, and the plot will look like this. So now we have in black the data for the mean overlaid on top of the other data. Let's go ahead and summarize the workflow that we did. We generated a table using the import function, and we called that function to import additional data of the similar type. We split our data by condition, we plotted our data for visual inspection using subplots, we then customized our plots, holding the axes, changing the names of different titles and X and Y labels. We computed a new mean data for each of those 2 conditions, and then plotted those data. So let's just recap. So far we covered the structure of functions, we talked about logical operators, we employed logical operators, We wrote codes and modified codes to create new plots, and we adapted automatically generated codes to import our data, plot our data, and compute new variables. For the next module, we'll talk about automating our codes further by incorporating loops and new functions we haven't discussed yet. Please make sure to complete the practice problems for this module before the session next time, and please come with questions.